I'm Clive Ayling, and thanks for coming back from lunch for this. A little talk, digital print for manufacturing. We decided we wouldn't talk about what we normally do at Meteor Inkjet. This time I would give a little talk about something a little different. So a very small part of what Meteor Inkjet really sells into. We make the electronics that people use in digital printing machines to make printheads work. And we've always gone for the stack 'em high, sell 'em cheap kind of area. So ceramic tiles, china, that kind of thing. And I've always generally kept a little bit of a distance over the last 20 years since I've been in it from projects like 3D printing, thinking that it was too early. But in the last year or so, we've been picking up new customers, almost one a month, in the area of making projects for additive manufacturing. And additive manufacturing is growing. The volumes of heads going into the area is growing, and therefore the volume of electronics. So whilst it's still a small area, I'll share with you a few of the things that we've been doing. Actually, a few of the technologies. I'm not going to talk all about my customers' projects. You heard one of them yesterday, actually, but anyway, about my customers' projects very much, because I leave it for them to do that. But we'll share a little bit about how we're generally taking stuff from 2D printing and putting it into 3D additive manufacturing. Now, 2D printing, I will obviously there's printing to shape as well, as we've heard quite a lot of today, which is not 2D, but it's 2D wrapped around something else very often. So wrapped around a cylinder, or maybe even a non-Euclidean shape, like it's curved in more than one dimension. But this is talk about 3D additive manufacturing. So I've got a few slides just to make it very clear. Obviously, it's not massive production yet, but the intention is massive production in this industry. So, fair enough. Yes, you can criticize me for saying it's not massively manufacturing, but it will get there, I think. And we're just seeing it come in. So a few slides about how Inkjet applies to additive manufacturing and where it doesn't. Next week I'm off to the Formnext trade show in Germany, where Inkjet will be a very small part of additive manufacturing, which is what the trade show is about. But nonetheless, it's there and it's growing. And I'm going to argue it's going to be a much bigger role when it hits proper production level than it does now, for reasons I'll explain. And then a few comments about where we've taken 2D technology and used it to solve 3D problems. Okay. So why Inkjet for additive manufacturing? Well, the same as you understand. You take a nice simple thing like a dispensing mechanism, and you can throw liquid across a distance onto something else. And that means you can put various fluids in. Now, as Zars just mentioned this morning, they've done something to expand the range of fluids that can be used, which is great. The range of fluids that were usable was great, and I don't think it was holding a bit back too much. But now Zars gone a bit further. Maybe we'll see even more fluids be used in additive manufacturing. And most of the challenges in this area are solved by new inks. And there's a whole bunch of new inks coming out. So there's a whole load of work required to make those new inks work. Those new inks, or new fluids, I should say, you've got to split them down very, very small. Why would you want to do 1200 dpi? I don't know. It would take ages, but apparently it's really good. I didn't know that, because you have too many big steps in your 3D object and you've got to file all off. It doesn't look like the 3D object you expect it to. So it slows everything down, but it also makes the result a bit better. Why would you want high viscosity? Well, apparently you can put more solids and things into the inks. These are all useful. So all of these areas are actually useful. You're trying to produce production. Why would you want picoliter volumes? You want liters. But we can shoot a lot of them, which helps. And some of our customers have got arrays of heads at 1200 dpi with thousands of nozzles per head. So you multiply that by this, and eventually it comes out at a decent volume. And you can start to produce rather than just do a sample. Obviously the big scale of machines we do in 2D, you take those scale across to 3D, everything slows down, but if you build something that big, you can eventually get something that produces a 3D item in a reasonable time. And I haven't put my customers' pictures up. So what I want to talk through very quickly, though, is one area where we found it easier for Meteor to help, and one area where we haven't helped so much, but where nonetheless people are working in. So Binder jetting is a kind of additive manufacturing where we're not adding we're not building the material out of the ink or fluid. What we're doing is we're joining the material together with the fluid which we're printing. So, and one of the most interesting areas which I came across a few years ago when I was travelling around my customers in China is sand casting. So they get a bed of sand, a very fine layer of it, and they join that sand together in a 2D pattern, and then they put another layer of sand on top and they do the same. And eventually you end up with a solid bit of sand which joined together inside a whole bed of sand that isn't. So you shake off all the sand that isn't, and you've got a solid object made out of sand, a bit like a gargoyle or something you might see sticking out of a church or something. It's sand. But the exciting thing is if that shape happens to be the inverse of what you want, you can use it as a mould. So you're casting your true material into that shape, and then you throw away the sand anyway. You break it all up. So sand casting is actually a very exciting, financially exciting area because you can make these fantastic cast shapes that would very quickly and very easily, digitally, straight from a 3D CAD through one of these machines. Instead of having to make mould tools, you can machine them and so on. So there's that one. And metals and ceramics is again, these are all of these different customers Meteor have picked up. They're all working on IP of their own, all working on some interesting new material of their own or new application. And this is where a lot of them fit in sort of joining together little bits of metal or little bits of ceramic to create some physical object out of the end of it. And then shaking away the stuff which they're not using. I can point at it. Look, this stuff here just gets lost when you shake out the solid structure that you've created in this box. So you have to imagine this is a slice through a large 3D object, a vertical slice through it. Material jetting, the other kind of half of where our boards are going to drive print heads to make these things work. So here we're actually keeping the fluid or the large part of it, but we haven't got any other material that's added to it. So there's no material there for just building up from the ground. So polymers, that's basically taking UV inkjet from 2D, but using the fact that it's got some height as an advantage. And metals and ceramics, obviously, this is somewhat different. You're having to lose a lot of the liquid because it's just a carrier. And then you have to fuse what's left as a later activity. But nonetheless, sintered metal parts, just straight from a CAD into production is fantastic. And a few years ago when I was a mechanical engineer, because you're right, I'm not a very good scientist, I was involved in designing something that was out of sintered metal, and we could come up with a fantastic little shape, and we could make it that way. We couldn't possibly have machined it any other way. And it was really an exciting tool, and that was for production. We were planning to make, thousands of these little shapes and stick them into continuous inkjet printheads that I was working on at the time. So there is a bit of a confusion, plenty of confusion actually, in the naming. 3D printing, that doesn't mean printing onto the outside of a bottle in this sense, nor does it mean generally extruding a molten plastic that you might do in your home printer. So all my neighbours, because I'm living near Cambridge, they're all techie types. They've all got their home printers, and they're doing that. And this is sort of good fun for these sort of purposes here. Well, this talk in this area is actually looking for more of a production environment. So we're worrying more about, can it be made efficiently? Can it be made for a short run rather than a one-off? So we're not trying to just make a model of what it is. We're trying to make the real thing, and we're trying to put that real thing into a real valuable product. And peace to Steve, not just to Formula One, but actually into a product that would be usable in volume. So here we've got a whole bunch more problems. It's got to be reliable. It's got to have a workflow integration. We've got to think about efficiency, stability. A lot of what Steve said this morning, his challenges to achieve that. That'll be the same challenge for my dozen other customers in their areas as well. They've got to come up with a process that works, not just a material that works. And yeah, we're not there yet. We're less than 2% probably of the already very small additive manufacturing, if you compare it to all the manufacturing in the world, is made with inkjet. But I don't believe it's going to stay at that low level. I think because inkjet's got these capabilities to do stuff, and there's such innovation going on at the moment, from universities to small companies to bigger companies, that are pushing through. I think inkjet will grow as a percentage of a growing market. So, what was it we heard yesterday morning? Someone said it's easy to overestimate how much there is going on right now, how easy it is to underestimate the future. I would agree. There is hype right now about the true value of how many heads and how many boards from Meteor are being used in this industry, but I still believe that it's going to ramp very fast. So I'm not sure we can make a living out of it right now, but we'll make a living out of it in the future. Inkjet, I think, is the technology that will be there because we can do production in a way that all those other technologies can't. We can ramp up. We have the ability to do volume. And we've got the proof, in a sense, in the 2D printing that we do, that we know how to do that. That the technologies can work that way. We support machines with hundreds of thousands of nozzles in them, 500,000 nozzles in one machine, I remember looking at. So, Meteor and the technologies we have here can scale, and you can build multiple machines which will pump a lot of ink, despite the holes being very small and the drops being very small. We can actually make a production volume of material come out. But yes, it is an expensive, complicated thing. So 2D printing, yeah, very commercially mature, I would argue. People can come to market with a new press. We saw some examples, again, in this conference, within a year or so. They don't have to develop the print heads, don't have to develop the inks, they don't have to develop the electronics, but you have to develop the process, you have to develop the application and many other areas. But you can do it in a fast time to market, a year, 2 years or so. Now 3D, yeah, some people are very sensible, got the right culture, might take 10 years, might take 20 years, but a lot of 3D, what we're looking for is how do we bring that down as short as we can? So how can we make use of the innovations, the knowledge we have already in the industry about 2D to take it up? So you've got in the 3D industry, we've got people going from extrusion, working their way downwards, if you like, into inkjet, and we've got people from inkjet, like Meteor, working our way upwards, trying to educate or trying to use our 2D technology in 3D. So transferable, what are we transferring? Obviously, the print heads transfer, whole range of different print heads, different pros and cons for each in this industry, and different enthusiasm probably from each supplier as to how they're getting involved, how quick they want to return on their buck, and how long the projects are. We've got some new improvements in the viscosity area in particular, and the heads are going recirculating for most of them, so we can now put some more aggressive inks into this application than before. So we've certainly got that, the area, we've got the sort of tools which the 3D world needs. If you want to get a strange ink to print properly, you can't just use any old waveform. You need to actually create new waveforms so you can get reliability out of your print heads. And we've got more technology coming in this area to tell you whether or not your nozzles are working correctly, for example, to get you the reliability you want. So these are all transferable stuff. There's other clever things like Czar's high laydown techniques to get lots of ink out very quickly from a small hole. What else we got? Yeah, so basically, my point is here that in our 2D printing, we've worked a long way towards getting technologies which can pump and pump and pump ink out very quickly. One area which 3D hasn't got their head around yet, I think, is grayscale. So we're working with some, but very few of our customers on how to put grayscale into a 3D world. Where would it have a value? Where wouldn't it have a value? So grayscale is when you choose the size of the drop, even though you haven't changed the print head or you haven't changed the nozzle. All you've done is you've changed the data going in, which controls the waveform. So you can push a big drop out of the same hole as you push a small drop out of it. So, and you can do that on a nozzle by nozzle basis. Any particular time, the nozzles out of the drops out of different nozzles can be different sizes. So that allows you to choose in each, they call it a voxel instead of a pixel in 3D, so a 3D pixel. You can choose how much liquid you're putting into that voxel. Now, the voxel may be exactly the same physical size afterwards if it's like a sand casting material because it's made out of sand. And all you're doing is put the binder in, but you can choose how much binder to drop into that cube of material. Here's another graph just explaining that. So in 2D, I think you all know we use this to make, instead of just black and white, we've got black, grey, and light grey and white. And in 3D, we'll end up with either small drops or big drops going into into that 2D pixel, which becomes a 3D voxel. So here's one area where what we've done for a customer is to apply grayscale into one of their issues. So in sand casting, the sand object, which you end up with, you want to have a nice hard skin to it, but inside that skin, you've got more sands. And why would you fill all of that up with your binder fluid, which costs a lot of money? What in fact you want is something like a lattice work on the inside, so the skin has got some strength to it, doesn't fall apart. But you don't really want binder everywhere, so you can have very small amounts of binder here, larger amounts here, larger amounts around the edges, and obviously no binder here because that's where the sand's going to get dropped off later. And you don't need that, you don't want that. So this way you can reduce the amount of fluid that you're using up to make the same object down to a very small amount by using grayscale in the concept, which they didn't have before. It was either, well, I've got to put it there because that's the bit I want to keep. But we could start going to them saying you don't need to. The other issue is, how would you create this shape? Well, you could draw it up in 3D. So your 3D CAD designer could draw every single little structure he wants inside it. And that's what he'd have to do in the old days if you were machining it. But for us, we don't need to. We just say, look, just tell us, just give us the overall shape. Guess what? We know how to use 2D rips to work out how to create this structure. So you give us the 3D shape, and we'll use our 2D software, we'll modify it, and we're using the skills of our sister company, Global Graphics Software, who write the Harlequin rip, to work out how we're going to identify skins, how we're going to create patterns on the inside using the knowledge that it's on the inside, how we're going to interpret that into different grey levels. So all of that work's done for our customer. They don't need to do it. They can stay in the 3D CAD world where there is just inside and out. We'll sort out the inside for you. We do that through rips and through the screening algorithms that the rips use. So screening is what we normally use inside a rip in 2D to make a difference in colour. Actually, each pixel is only one of 3 colours, but we manage to get many appearance of many colours if you stand far enough back. So you can use that a little bit in 3D. If you can have a smoother surface by using grayscale, that's great. But also the way in which we do this, the screening technique, we can use that to create lattice structures and so on for people. So they just give us the outside, we screen it, we produce the inside for sand casting. Another area where we're applying screening and grayscale is in the creation of 3D objects that have a variation in material from one place to another. So you can vary, if you have multiple print heads firing with different, say, for example, colours, but it could be some other purpose like DNA or something like that. You can end up with a sort of fine gradation of change along something rather than a sudden transition between one item and another. So again, we can take this challenge out of the CAD world, leave it in the Inkjet world, and solve that for people. Here's another one, image that was used for when we were the sand casting one. So again, here in this one, we had a fairly thick skin on the outside, and then we had a medium level for the lattice, and we had a low level for the sand that was trapped inside the lattice, inside the body of the object. You have to imagine I've cut a hole in it here so you can look into it. Obviously, it had a seal on the top normally, so you wouldn't see this on the inside. I think if I've got 2 minutes left, I might have. There was one other area I was going to mention, which I didn't have time to draw a slide about. We had one customer who's printing on a toroid. So they're printing here. They're laying down more more material here. This is the binder, this is the material, and they're travelling round and round continuously. And we realise that the resolution of a print head here and the resolution of a print head there are different because the different distances to the centre. And that was completely analogous to printing on cups and bottles, conical cups and bottles. The same challenge. The print head sitting here, the resolution here is different from the resolution here. So solving, again, the 2D, it looks like a 3D challenge, but a 2D printing on the outside of a 3D object, the software which we use for that, we could convert into software which a 3D printer needed to be able to print on their continuously layer building structure. I may have explained that too quickly, sorry. And then lastly, there's the workflow issue. I talk about making this production solution. You've got to have an automated workflow for production. It's got to work very quickly through without having to go from one stage to another. So 2D workflows, I think everyone in the room would recognise some kind of creating your image, some kind of editing it into the pages, RIP, again, hopefully Harlequin, because it would help my bonus, and then into the inkjet printer system, hopefully with Meteor, but anyway. In 3D world, the first stage is not a label designer or a bottle designer or something, it's 3D CAD. So your 3D CAD guy designs this, whatever it is, children's boat or something. And that output has got to be absorbed by something. A whole bunch of companies sort of play in this area, Dendrite, Core, and so on, Materialise. Some of them, well, most of them from this area, and most of them very heavily funded by an awful lot of money on the stock market. Sadly, my pension funds probably. So this area is loads and loads of software work going on from people who either came from gaming or came from 3D CAD, and they output slices, so a layer through there. And then working up from this end, which is where Meteor and whoever that is, Rico's are, I think. Anyway, the printhead vendors are at this end with Meteor, and as I say, things like rips and screening. We have to work our way back to help. So somewhere around this point, Meteor's met our customers going this way and we're going that way, and we try and resolve the remaining problems to get the workflow to work straight through. So what we're looking for is very high-speed slice processing, because as I say, we're going to have to use thousands of nozzles very, very quickly. Every image is going to be different. Thank you. And working out a 3D workflow and building it for our customers is the work we've been picking up for the last year or so since we got more interested in this market. And that, I think, is pretty much the end of my presentation.
Thanks so much, Clive.